Yes, thank you, Sergey, for the warm welcome. Just before I start, please let me know if drops or the connection drops, because I'm not sure if I have excellent internet connection, but I think it will be fine. Okay, so let's talk about my PhD work. So one part of my PhD work focused on stability analysis in discrete event systems, and specifically the ones that can be modeled in max plus algebra. So there are three parts to this presentation. So three parts to this work. So what you see here are three keywords. One is discrete event systems. Another one is max plus algebra. And then there is stability analysis. So we have discrete event systems, and it is obvious that we study stability notions coming from discrete event systems. I will divulge already in the beginning that the analysis tools I use are coming from conventional time-driven systems. And I use max plus algebra to model the system, and I also use several optimization and analysis tools from max plus algebra to study these stability problems. So let's just begin with a very simple example. What we have as a discrete event system is any man-made system that progresses over events, and these events can occur asynchronously over time. So for instance, this is a production line, and what we have is that it has two processors. So we have M1 and M2, and we can assume that some raw product is coming in and it is going out from M2, and this is just the first mode of operation. And the second mode of operation is the complete opposite. So we have the raw product coming in to M2 and it is going out of M1. So how we model these systems is we look at the time of processing of this raw product into the final product. So what we have is that a job coming into M1 takes 4 units of time to be processed. It takes 1 unit of time to be transferred to M2. And at M2, we need another 1 unit of time to process it, and then it exits the system. And in mode 2, it is the other way around. It comes into M2, and then we have the corresponding times denoted on the figure. So what would stability mean in these systems? One of the common ways to study stability in discrete event systems is to look at the overflow of buffers. If the buffers are going unbounded, then it means that the system is unstable. So what do we mean by buffers? So we would consider a buffer somewhere here between M1 and M2. For the time being, we assume that there are the size of the buffer before M1 and after M2 is infinite. So we consider that M1 is actually a bottleneck of the system. So we have 4 units of time being consumed to process the raw material. And at M2, we have 1 unit of time. So if M1 is slow, that means that whatever gets filled into this buffer will be immediately taken out by M2, and it can never overflow because the rate of incoming material is smaller. So what happens if this 4 is actually equal to 1, and this 1 is actually equal to 4? So this is a typical case where I have the buffer getting overflowed, and what it means is that the system is unstable. And for these simple systems, it is very easy to notice these problems that the system is unstable, and such production lines, such this is just a small part of a discrete event system. So these problems occur a lot. And we can already imagine that this is just one mode of operation. And if we switch between these two modes, the system can actually be unstable in some cases. So for modeling purpose, all we have to note here is that there are two kinds of operations that are being done here. So the first one is that whatever comes into M2 is 4 units, so 1 unit of time difference from when it left M1, and 1 unit of time difference from when it was when the last material was processed at M2, so in the previous cycle. And we consider that every job is given a counter. So we count it like that, and that gives us the event counter. And we can model the system in max plus algebra. So I'll come to that part later on, but for now we can just see that in mode 1, we can write x1 for kth material, kth event, as x1 k minus 1 plus 4, 4 being the time that it took to process the previous material, and x2k is just the maximum of x1 k minus 1 plus 1, which is the transfer, and x2k minus 1 plus 1, where 1 is the processing time at M2. And what we notice here is that we have an operation maximum, which is synchronization. And this plus is actually just a delay operator. So we have a time delay in the system. So what we can do now is look at what stability means when we model these systems in this algebraic format. So here F, I say, is vector field going from Rn to Rn with defined for every Lk. So for mode 1 and for mode 2, and they take like this max plus format. So that's what I mean by max algebraic. And this is a discrete event systems defined for event counter K. And what I see when I plot the processing time, so the time xk at the two machines, x1 and x2, M1 and M2, and then what I see here is that there are two kinds of bounds that I can study on the trajectory of the system. So one of them is the growth rate that is given by this slope, that is like an average slope of these trajectories, which gives us the inverse of the throughput of the system. So it would tell us how many products we can produce per unit time. And then we have the bounds that are placed at a particular event K. So let's say at K equals 4, we would like that the maximum and the minimum of the time occurrences of the events is bounded with respect to each other. And this usually shows up as a make span in the system. So time from the initial activity to the final activity with respect to a particular product or particular event. So moving on, it is important right now to notice that we need some sort of measure on the state X that allows us to calculate this width or this difference here. And this is not really possible in the existing norms. So one of the ways is that max plus algebra provides Hilbert's projective norm, and it's what it does is that it calculates the maximum of the state minus the minimum of the state, which is indeed what we need, and it gives us the width that we refer to here in the state X, the plot of xk. And what we see here is that we can, why this is a projective norm is because it works on the projection of the system. So it is invariant to translations of the state. So for instance, I can, if I have xy in R3, I can project it on x3 equals 0, and I can translate it with x3 equals 1, 2, 3, whatever. And what we will see here is that this block here, that is the unit ball, it translates linearly with x3. And what you see here is that it is being plotted on a hyperplane that is x3 equals 0, which is in strike contrast to the L infinity norm, which is just a hypercube in the hyperspace, in the R2 or R3, whatever. So moving forward, this we now look at what happens if there is only one mode. So right now we considered that there are two modes. What happens when there is only one mode is that we obtain a max plus linear model. And what I mean by that is I can model it as a linear time invariant system or linear event invariant system in the math algebra. And this is a very nice way to study a lot of problems that arise in discrete event systems. So one of the properties are mainly that it is defined on a space R, R epsilon actually, and then it has two operations, O plus and O times. O plus is just the maximum of two scalars, and O times is the addition. And then we can also define the unit element E equals 0, and the epsilon element, which is the 0 element in the max plus algebra, which is equal to minus infinity. Similarly, the matrix vector operations can be extended to max plus algebra. So what we have here is that we will multiply 4 and 0, which will be 4 plus 0, and we'll take a maximum with 1, 0, that is 4. And similarly, for later on, we look at even vectorization operations that that can be extended to max plus algebra from conventional. And this is really nice. So we can easily extend a lot of tools from conventional algebra to max plus algebra. Okay, moving forward, how we study the stability of max plus linear systems is that we can look at the fixed point problem of the system. So the problem of stability boils down to the existence of the fixed point of this AO times X. And this is nothing but the max plus eigenvalue problem for the system, and that I have written down here. So we say that there exists a vector in Rn that such that AO times V equals lambda O times V. That is the max plus eigenvalue problem, and this is also the simply the fixed point equation for the here is that if there exists a V, then we can say that there is a fixed point, and I'll tell you why this directly correlates to stability. So one of the conditions for existence, so this is only a sufficient condition for the existence of the eigenvector, is that the matrix A be irreducible. Again, it is only sufficient. The examples that we looked at in the beginning of the presentation involve reducible matrices, but they had a finite eigenvector. Okay, so why does this existence problem translate into stability? So there are mainly three properties that are important, and as we see that additive homogeneity is in a discrete event system context, it means that if we translate the starting times of the processing at each machine linearly, then the finishing times will be scaled linearly as well. That's the main idea of additive homogeneity. And then we have monotonicity and non-expansiveness, and these two properties are equivalent to each other if the dynamics is additively homogeneous. So if we have a monotone dynamics that is additively homogeneous, then it is also non-expansive. So what we see here is that if there exists a finite vector that solves the max plus eigenvalue problem, then any trajectory that starts that starts at a particular distance from B will never diverge from that trajectory FV, because FV is in the end equal to lambda O times V. So this is indeed a fixed point, and whatever other trajectory there is will never diverge. And this is, in a sense, a stability property. So I'm not talking about attractivity here. So it can happen that I cannot start anywhere and reach this max plus eigenvector, but it has a certain stability property. Okay, moving forward, what I look into is switching max plus linear systems. So we are looking at hybrid systems in max plus algebra. Why this is useful is that it allows us to model choice, the phenomenon of choice in discrete event systems. So far, max plus linear systems only allowed us to model synchronization and time delay. What we can do by changing the matrix A is that we can have different modes of operation being modeled by the same description, mathematical description. And here phi is just some function, and v of k we assume is random. So in a sense, the switching is random, or not random, it is arbitrary. And what the problem is that the assumptions don't hold. So the assumption of additive homogeneity still holds, but it is not necessary that the assumption of non-expansiveness of the dynamics holds for the case of SMPL systems. So in the end, we can actually, whatever methods I study or whatever framework I propose later on in the slides, can be extended to system dynamics that are max plus algebraic. So I would like them to be continuous in X for a fixed L. I would like them to be structurally finite, which means that there can be an epsilon here, but what I would like is that if I start with a finite state, I remain in a finite state, and which means that if I have started working on a machine, then it cannot, the time of occurrence of the next event cannot be minus infinity, which would mean that it's occurring, it's in the past somehow. And finally, I assume that it is additively homogeneous, which, as I explained, is a simple linear translation of times. Okay, moving forward, let's see. First, I would like to discuss notions of stability in conventional systems so that we can understand how they can be translated to the systems, discrete event systems. So generally in conventional time-driven systems, we are given a normed space where we have a norm on Rn, let's say, and we are given an initial condition. Let's consider an autonomous system, no switching at all. And the Lyapunov, in a Lyapunov sense, the stability is usually given with respect to a fixed point. And the stability here, for instance, it means that if I start very close to the equilibrium point, I will always remain close to the equilibrium point. This is a crude generalization, but this is the idea of stability. It's in a sense non-expansiveness. But as you can see, if the norm makes a very big difference. So for instance, if it's an L2 norm or vector norm, then we would have a ball in higher dimension, and we would talk about the contraction of these balls. But right now, what we have is Hilbert's projective norm, and we cannot talk about balls in a way because it's actually working on rays of a cone. So we'll see how that works on later on. But we have stability notion, and then we have the attractivity notion that eventually that the state xk converges on the equilibrium point. So in general, we can exchange this x star with positively invariant set, and I'll come to that later on, and that would be the topic of study. Okay, so one of the other notions that we study is ultimate boundedness, which is just that we always remain bounded with respect to the equilibrium point, which can be 0, for instance. And what we are interested in is the max plus algebraic notions of stability for discrete event systems. So for instance, right now, I would only consider the boundedness of the state at each event k. So I'm only looking at this width, this difference here. So I can calculate this using the projective norm. And now I have restated the Lyapunov stability definitions using an invariant set. So I have that, first of all, there exists a set K such that it is positively invariant for the dynamics. Then I would require that it is attractive, that that any trajectory eventually ends up inside the set K. So actually this should be the curly K. And I have an ultimate bounds. So this is a totally different one, which just says that in the end, if I would like to have max plus bounded buffer stability, I need to have some bound on the elements of the set K. So I would like this to be bounded in the projective norm. Okay. So the stability problems that arise from the Lyapunov framework are mainly the ones that I looked into are mainly 3. So the first one is, do these sets always exist? So what are the conditions for such invariant sets to exist for a set of matrices? So here I'm only studying a semi-group of matrices in max plus algebra. Another problem that we study is the construction of such common invariant sets. So if they do exist, then can we construct them? And the last one is, can we determine if such sets are attractive? So again, so can we determine that the trajectory eventually ends up inside the set K? And such problems have been studied for max plus algebra, for max plus linear systems, but there is no concrete theory to extend it to a larger class of systems that arise from, let's say, introducing choice in discrete event systems. So moving forward, I'll first discuss some well-behaved invariant sets. So some really nice sets that are that we can manipulate both in conventional algebra and in max plus algebra, and that helps us a lot. So what we look into is a max plus cone. It should be finitely generated. That's our interest, so which means that it has finitely many generators, and it's just an analog of a convex cone in conventional algebra. And then we require that, so there are certain max plus cones that are of interest. So the first one is the max plus eigencone. So for any function g, we can construct a max plus eigencone that is a super eigencone and the sub eigencone, and we can study it in the properties of this function. So for example, I have a paper in a conference where I study invariance with respect to these max plus eigencones. So there are some conditions on this function g. So there is, let me go on, that for instance, I can assume that this g of x is max plus linear. So for the simplest case, I can just assume that this function is just q o times x, which is max plus linear, and I can generate the eigencone using this simple matrix q, and I can, for this simple case, it's just the max plus summation of these two matrices, and I can show by very simple arithmetic that this is actually positively invariant for both the matrices. We can generalize this function g to a more complex one, which is determined by, let's say, this constraint automaton. So this is an automaton, and what I say here is that if I am in Q1 then and I apply A1, then I will stay in the cone Q generated by Q1, and similarly. So what the difference here is that this A2 matrix is unstable. So I cannot have stability under arbitrary switching. So I would have to look for some constraint on the switching sequence. Okay, moving forward. So the sets that are generated as max plus eigencones of for max plus linear matrices can be described as using clean star matrices, and that's the easiest one to describe, and I would restrict myself to such sets in this presentation. So the main property here is that they are equal to their clean star operation. So this is a clean star operation. It gives the longest path, and well, it's basically requires that the eigenvalue, max plus eigenvalue of this matrix K should be smaller than 0, and then it exists. So we can generate what I call max plus C sets using such clean star matrices. So what I require apart from such max plus cones generated as column using the columns of the clean star matrix is that they have a compact projectivization. What I mean is that when I plot using the Hilbert's projective metric, the resulting figure is compact. And this can be achieved easily by requiring that the matrix K be irreducible. And the nice part is that such sets are also convex in the conventional sense. Okay, this is a small detail. We can represent the Hilbert's projective norm using clean star matrix. So the first problem that I proposed to study was the existence. I think I will come to the existence problem later on, because I believe it's a difficult problem in general. But what I can say is that if it exists, then there are ways to construct such matrices, at least by assuming that it's in this clean star form. So the first result that I presented is on positive invariance. So there are already theorems on proving that a given set K that is finitely generated is positively invariant for a single matrix. But I found that such the theorems that were existing were not constructive. And I'll show what I mean by constructive later on. But here we have that I call this the S lemma, which shows up in implication of quadratic inequalities in conventional time-driven systems. And what we have is that this requirement of positive invariance is equivalent to these equations being these equations holding for all the matrices AL. And as you can see, the matrix K is So this is more like a quadratic, not quadratic, but like a bilinear format. If you look at it in max plus sense, it's not really linear. And however, we can parameterize this matrix K because we know the properties of we know the properties of a clean star matrix, so we can easily parameterize it, and we can solve for this matrix using mixed integer programs. So for instance, I have a sample piece here where I minimize, I would like to know the smallest common invariant set that is not empty. So I minimize the volume of this matrix K. A matrix K would be something like zeros on the diagonal and some elements on the rest of the elements. And then I would minimize the volume of K, and I'll tell you what I mean by that. But the constraints ensure the following things. So the first constraint, set of constraints, ensures that the matrix K is positively invariant for all the matrices AL. The second one ensures that that this is an idempotent matrix. So for instance, a property of clean star matrix is that K square in the max plus sense is equal to K. So the second constraint, in a sense, ensures that. And what the rest of it is that it's just I parameterize all the elements of K. So I assume that it's completely parameterized, so there are no epsilon elements. And I calculate this eigenvalue that I call lambda 2. So here I call it lambda 2 because this is not the largest max plus eigenvalue, but this is the second largest max plus eigenvalue. So I would solve generally for the max plus eigenvalue by also having including the terms for I equals j. But here I do not include the terms for I equals j because they are on the diagonal, and I know for a fact that the largest max plus eigenvalue of a clean star matrix is 0. So therefore, I only look at the second largest max plus eigenvalue, and this max plus eigenvalue is a representation of the volume of this clean cone generated by this clean star matrix. I can explain this further a bit. So for instance, I look at matrix scaling where I only scale the non-diagonal elements, and I can scale them up to a point such that mu is greater than minus lambda 2k. So I subtract mu from each and every element, non-diagonal element of this matrix. What happens is that I start with this bold line, which is k0. And as soon as I start decreasing mu, I go inwards to the center of this set, and which the center denotes a matrix K that has only that has a dimension of 1. So the weak max plus dimension is 1, and I can obtain that the representation of that point in a matrix format by subtracting minus lambda 2k. Therefore, this minus lambda 2k represents the diameter of this set somehow. So this is a very good representation of the volume of the set, and I can minimize the volume by maximizing minus lambda 2. And I can solve this problem to obtain the common invariant set. So moving on, the next part is the attractivity. And attractivity, here I talk about contraction. So far we were talking about positive invariance, but here I talk about contraction. So what I mean is that we look for, so let's say start in K delta. So there is a set delta, and I start with K delta so that this is K, the one in the center, and the one outside is K delta. And I say that what is the fastest, what is the slowest rate of growth towards K? So what is the largest mu that is smaller than equal to delta, such that xk lies in K mu for whatever xk minus 1 I choose inside K delta. And this I can formulate as a parametric mixed integer linear program, where I have maximization over mu. The first set of constraints denoting that that x of k is in K mu. The first set of constraints denoting that x is in K delta. And I maximize over mu. So this is actually a mixed integer linear program, and there are many papers on this subject which using which I can prove that the optimal value of P delta is monotone, non-decreasing over delta. So what that means is that if I can prove that this parametric MILP is feasible on a set 0 to delta max, then the system is actually attractive. So the system is the trajectories are attractive for this set K is attractive for trajectories of the system. And the nice part here is that if we fix delta, then we can see that this is AX smaller than equal to BX, because we already know what K is. And this is a reformulation of a tropical linear fractional program, so fractional linear program. So, and then there are, I solved it as an MILP, but this can also be solved for particular instances using tools from mean payoff games. And so there are some examples of I just used some grading methods to solve this as MILP, to be honest, but it shows promising results. What I have here is that the trajectories decrease for one step, and if I take 2 steps, then the trajectories decrease. And so what this means is that I always go into this set K. So this set generated by the columns of this matrix K are attractive for the initial production line system that we started. So finally, for the first problem of construction, I could not say much then, but what I can say is that I can use tools from vectorization to reformulate the problem of positive invariance into two-sided max plus non-homogeneous equation. So here I have Z1, which is vectorization of K, and this is a Kronecker product with vectorization of K and vectorization of K on both sides. And because I assume it to be fully parameterized, this elements are finite, and I can solve for Z1 and Z2 using some alternating method. So at least I can show if there exists a solution or not. So that answers the first problem that I referred to earlier, that can we say that common invariant set exists. Okay. In conclusion, I presented Lyapunov stability framework for discrete event systems in max plus algebra. I used that framework to study the boundedness of matrix semigroups in max plus algebra, and I also came up with some MILP tools, algorithms to solve some of the underlying problems. And although MILP is NP hard, but as we can see, there are formulations of those MILPs that are known to be tractable in a sense. They are not that bad, and we can look into the relationship of the algorithmic framework with tropical optimization. So for the future work, I would say that I'm still looking into the extension of the stability framework under constraint switching. So I hinted towards it in the path complete stability format, and that can be looked into. So once everything is inside this Lyapunov framework, then there are tools in the conventional time-driven setting where that can be used directly. Or so this is a really nice result, in my opinion. And I would also like to extend the results for continuous valued under continuous valued inputs. Finally, in the algorithmic sense, I looked at the existence and construction of common max plus invariant sets, but we can look at the existence and construction of multi-cones, so multiple max plus invariant sets. And we can also look at efficient solution methods for the optimization problems I studied. Thank you very much. I would welcome questions from the audience.
Great. I think, of course, let's thank Abhimanyu for a great talk.
Thank you.
And was very nice for me to see. Let's take questions from the audience first. Does anyone ask? Does anyone have a question